Okay, hi everybody. Prove that this curve wraps around the unit circle at unit speed. Okay, so first of all, let's just remind ourselves that theta here is a real number, and this is a complex number. Although, in this symbol, it's not apparent, like, what's the real part? What is the imaginary part? Can we write it something like this? We have no idea because this symbol wraps up a ton of complexity and hides details. Okay, so we have to work with what the symbol actually means to prove these things. So this is a complex number, which is just R2. Okay. All right, so first of all, to show that it's actually on the unit circle is just to show that, claim for all real numbers theta, we have e to the I theta absolute value is 1. That is what it means to be on the unit circle. So that the image of this map is completely contained in the unit circle, which means that the modulus is 1. Okay? And so let's try to prove this. So first of all, so I guess proof. Recall that the modulus of a complex number can be computed by doing the square root of the complex number times its conjugate. Okay, so in the case that our complex number is an easy, we actually know the real part and we know the imaginary part of our complex number, what this says is that it's equal to the square root of a plus bi times a minus bi. That is the complex conjugate. When we actually know the formula for our complex number. And square root. So let's look. And sure enough, we get a squared, abi minus abi cancels, and we get a bi times minus bi is a minus bi squared, which is exactly what you'd expect from Pythagorean theorem. Okay? But that was just to remind you, what does this even mean? But now the problem is that we have what complex number? We have this complex number. This is not a plus bi. It's hiding. We have no idea what this is. But we can still write, and then conjugate, square root. Okay, and now first claim is that we can replace this thing. And I claim that when we look into the details, the complex conjugate is just, you put a minus I there. This is not obvious at all, so we need proof. Proof. But then once we do, now we're going to see that the reason we write this ridiculous notation that hides all this complexity is because there are exponent rules. When we can add the exponents. I theta plus minus I theta is in fact 0. And e to the 0 is actually 1 because it's, plus 0 plus 0 squared over 2 plus 0 to the third over 3 factorial plus ... And the limit of the sequence of partial sums is in fact 1. Okay. So this also needs proof to go from here to here that we can add exponents. So let me say what we need proof. Prove that e to the I theta conjugate is just e to the minus I theta. That we need to prove. Then right here we need to prove something. Prove that e to the x plus y is e to the x times e to the y. So that we need to prove. I guess that's it. Is that really it? Then we've got the first part, that it's on the unit circle. And then we also need to do unit speed, but we'll do that later. Okay, so let's first let's prove these two things. So this one See previous problem. Okay, so that's literally one of the problems that we already know how to solve. So let's do this one. Okay, so why is this true? So first, let's recall that the symbols e to the I theta are defined to be the limit as m goes to infinity of certain partial sums, where Sm is a sum, a finite sum, from n equals 0 to m of what? Well, this thing, instead of x to the n over n factorial, we plug in x equals I theta. I theta to the n over n factorial. Okay? So quite literally, like for example, S5 would be 1 plus I theta squared plus over 2 plus I theta to the third over 3 factorial plus I theta to the fourth over 4 factorial plus I theta to the fifth over 5 factorial. And you see that it is not clear at all that this number will be on the unit circle. Like, it is not at all clear. But it is, so let's keep proving it. Okay, so recall that this is true. This is the definition of these symbols. Okay, now, so maybe I'll switch color. Then, what are we trying to prove? We're trying to prove this. So e to the I theta bar is just the limit as m goes to infinity of the S sub m's bar, which is equal to the limit as m goes to infinity of the S sub m bars. And let's look at what that is. So first we should probably justify this, but we'll justify that in a second. First, let's just see what this is. Now, what do we do here? Well, we take the conjugate of what? The mth partial sum. Now, remember, the conjugate of z plus w is the conjugate of z plus the conjugate of w. And also something like z to the n conjugate is just the conjugate of z to the n. These were elementary properties of complex numbers that we looked at a long time ago. But what does this give us? It means that we can take this bar and it's going to go inside and hit the I. Theta is a real number. N is a real number. N factorial is a real number. So what we have is that an I becomes I bar, which is just minus I. Okay. And so what we have here is that this is now a limit of m goes to infinity of what? Well, it's the sum, a partial sum, of something where the I becomes a minus I. And then look at that. That is actually the definition of e to the minus I. Right? We just plug in, instead of x to the n, we plug in minus I theta to the n. Wow, and we're done. Okay. Now, there's one more thing to justify here, which is, why is the conjugate of the limit equal to the limit of the conjugates? Well, let's look at sort of a picture proof of this. So here's my picture proof. I believe also this was proved in chapter 2, but let's say here's the complex numbers, and let's say I have some sequence that is limiting to this limiting value. Okay, so right here is the limit of the S sub n's, and here's all the S sub n's. Okay, well then, where is the conjugate of the limit? Well, the conjugate of the limit is down here. The limit of the S sub n's conjugate is down here. You just flip. That's how you conjugate a complex number. Oops. And now, look at, if you just take all the S sub n's and conjugate them, you'll get something like that. What are all these? This is a new sequence of just all the conjugates. And that's exactly what this equal sign is saying, okay? So you could prove this in more detail, and the exact same value of, you could choose epsilon or choose d in r greater than 0, and there exists an n because the limit of the s of n's is some number s. In other words, because this is a limit. And that same n will work to show that the limit of these is this number. It'll be the exact same n will work, but we're not going to go into all that detail. We did that already. We can graduate. Okay, so now we've proved this, the first part, and we proved this part in some other problem. And so now we know that this curve indeed wraps around the unit circle. Now we don't know how it's wrapping. So let's look at, here's the unit circle in the complex plane. All we know is that e to the I theta is always on here. But we don't know, maybe it starts, well actually we do know that e to the 0 is 1. So at time theta equals 0, it's right here. And we have no idea what it does. Maybe it goes like this and then turns around and goes around and then goes like that, and then always staying on the unit circle but maybe doing crazy stuff. But it turns out it doesn't. What it actually does is it just goes around at unit speed, at exactly unit speed, around and around. Okay. So let's now prove that at unit speed. Why unit speed? So proof. So take the derivative. So take d theta of e to the I theta. It is tempting to say by the chain rule, we get an I coming out, and then e to the derivative of e to the I theta is e to the I theta. Or the derivative of e to the x is e to the x, but we need to prove this, okay? So let's look at what this means. We're going to take d theta of what? A limit, as m goes to infinity, of 1 plus I theta plus I theta squared over 2 plus I theta to the third over 3 factorial plus dot 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 plus I theta to the m over m factorial. And so remember, for power series, we can actually just differentiate term by term. And so I guess what that really means is that the derivative passes through the limit. In our book, we prove that you can differentiate power series. And so here we go. d theta applied to all this stuff. Okay, let me just... Now, what do we get? Well, we get limit as m goes to infinity of what? So the derivative of 1 with respect to theta is 0. The derivative of I theta with respect to theta. Derivative of this with respect to theta. Well, theta squared becomes a 2 theta when we take the derivative. Everything else hangs out. So in particular, the I squared hangs out. The theta becomes a 2 theta and cancels the 2 down here. Okay. Over here, similarly, we get a 3, canceling that 3, leaving a 2 factorial. So this 3 factorial becomes a 2 factorial. We still have 3 i's and a theta squared. Theta to the third becomes 3 theta squared. The rest hangs out and cancels. And etc. To the mth term. And what do we get? Well, limit plus infinity. Well, let's pull out an I. We get a 1, an I theta, an I theta squared over 2 factorial, and finally an I theta to the m over m factorial after we pull out that factor of I. And sure enough, this is I e to the I theta. And we're done. Well, no, we just showed the derivative is this, okay? Now remember, what does it mean to multiply by I? It means rotate by 90 degrees. So if we're on the unit circle and we're at e to the I theta, what is That's a two-dimensional vector. It's a complex number. And we rotate it by 90 degrees. That gives, well, it gives us, I guess, this complex number. But then we're thinking about that as the velocity. And sure enough, at any point, we just have, it's wrapping around the circle. And what's the velocity of a circular motion? It's tangential to the circle. And so this is the velocity. Now, the velocity is fine. We wanted unit speed. So what is unit speed? So we're asking, what is this? Is this 1? Well, sure enough. The absolute value of I is 1. And we already proved that the absolute value of either I theta is 1. That is how we showed it was on the unit circle. And so this means unit speed. Awesome. Okay, that's it. We have finished our proof of the geometry, matching the sine and cosine geometry. An angle is the length of this circular arc. And we proved that this curve actually exactly encodes that geometry. Now that's great because the real part and the imaginary part have these explicit formulas. Yes, they are infinite series, but they are absolutely convergent. And so we can plug in anything we want and get any cosine and sine that we, to our heart's desire of accuracy. This is great. Make sure you understand what's happening here. When I plug this in to e to the I theta and I take the real parts, I get all those. I take the imaginary part, that's the previous video. But you see that I squared is -1, so the I goes away. I to the 4th is 1, so the I goes away. So this is all the real part. Every even power is the real part. Real, real, real. That will be real. The 8th power will be real, etc. The odd parts have an I, a minus I, an I, a minus I. And so if we just pull an I out, then we're just left with plus, minus, etc. And that's sine. Okay. Can you do this yourself? If so, you will really understand complex numbers, and I guarantee that when complex numbers occur next, it will probably be something to do with this formula. So this is worth your time. Okay, can you do it? Blank sheet of paper. How do you prove this?